So the motivation behind this particular project is really questionable. So basically I was thinking, what would happen if you put a tree or a couch or any sort of everyday object as a potential in an infinite well situation? And that's a really poorly thought out question because it doesn't make a lot of sense. But it is kind of interesting to think about different potentials that are easy to calculate on a numerical basis, but really complicated on an analytical basis. So like if you were to calculate out the potential of a chair or any sort of everyday object as an infinite well in a quantum situation, that's a ridiculously hard problem on an analytical side, but it is actually fairly straightforward on a numerical side. And so I was kind of curious about being able to do this, and then my brain just went to what if this could all be live and you could just have a video stream of whatever you're looking at, convert that into a depth image, put that depth image onto like a faraway computer that can calculate really fast, make it calculate out what the eigenvalues for that depth image would be if it was an infinite well, send it back to your computer or your cell phone, and then have your cell phone display the eigenvalues in semi-real time. So I think I can get this down to a second. I think this should all work out. But the motivation, you can see how it kind of slid a little bit there, and it's in the end, it's not super well motivated, but it's a really fun project, and I think there's some things that it can be extended to that actually would have some value. So let's just start with this, and then maybe we can look at some other differential equations that might be a little bit more pragmatic in the future. Because the eigenvalues of a chair is just a dumb question to ask. This is differential equations being used on depth information. And so the phone takes in depth information, so how far away objects are from the phone. That is converted into a mesh, and then that is used to calculate out differential equations. So in this case, we are using the Schrödinger equation that is static, so not the time varying one. I wanted to go a little bit over how I actually represent a wave function. And so largely I am just sampling from it, and I'm getting an imaginary number. And so imaginary numbers need to be represented somehow. And so I tend to use size for magnitude and Q for the actual phase information. And so if you were to plot the imaginary versus real part onto a graph, it would look something like this. So we have, as you get further out from the origin, all the particles get larger, and then as you go around, it changes colors. And the reason for doing this has to do with how E is structured. So for E, larger values of imaginary values just kind of rotate your value around the complex plane, and values that are larger will end up being further out. And so this makes a lot of sense for representing a wave function because larger values will have a larger magnitude, and so there's a higher probability the particle will be there once you've done Born's rule and all that. So that's why it makes sense for them to be larger. And then the color is something that will impact how it combines with other wave functions, but it is less important to the actual magnitude because that information will disappear with Born's rule. And so it is only important as a difference between the other phases. So phase is always important in relative terms in quantum mechanics. The absolute number doesn't matter as much. Strangely, this does actually have a little bit of an application. Quantum dots are really small objects that you have to calculate out wave functions for. So in principle, you could start figuring out some wave functions with different shapes of quantum dots. But that's not why I did this. I have another video that kind of explains the calculation for Schrödinger equations. That's here. This code is basically just putting that into a Django view so that it can be called from a server. And so basically running it through, we have a lot of the similar setup. And then each time the event is called, there's a request that's made. The request ends up here. We split it into the image, the eigenvalue that's being requested, and the pose. And so this is very similar to the potential. Split apart the pose and then put it into the potential and calculate out the potential that way. And now that we have a potential value, we can just plug that straight into the Schrödinger equation and use the kinetic term that we had previously done, solve for that, and then we can just shape it into the wave function that we are using. And here we're just turning it into a real function, multiplying the Schrödinger equation by a phase value, like multiplying all of it together by a phase value is something that is allowed because quantum mechanics is invariant if under phase addition or phase decrease. Like if you multiply an entire wave function by a phase. This is getting a little bit beyond the scope. So we are doing a similar fetch loop that we did with the potential. So we are gathering our information together, sending it to the server, and then when we get the information back, which will be the wave function, we will update that, and we will update both of our eigenvalue distribution and our wave function image. And so that'll give us an idea of what our energy spectra will look like for these particular weird values, and then it will also give us an idea of what our wave function is like.